Hi everyone, I'm Emily and this week we're working on drawing Lewis dot structures and determining polarity. The question is asking us to draw the Lewis dot structure of carbon dioxide and sulfur dioxide and to determine whether each is a polar or non-polar molecule. So let's go ahead and get started and let's do the Lewis dot structures first. So carbon dioxide, the way I do the Lewis dot structure is I start by adding up all the valence electrons in our structure. So carbon has 4 and each oxygen contributes 6. So we have a total of 16 valence electrons in our structure. The next step is to draw the central atom and connect all the atoms together and give everything a full octet. And let's count how many we have. We have 8 over here, so 4 and 2 and 2, so 8, and then 6 and 6. So 8 plus 12, that's 20 valence electrons. So that's 4 more electrons than we're supposed to have in our structure. So that tells us that we need to have double bonds in this structure. And there's a double bond there. Now if we count, we have 18, we still have 2 extra, so we have to go ahead and do another double bond. And there we go. And that's the final structure of carbon dioxide. And its molecular geometry is going to be linear. Now for sulfur dioxide, if we go ahead and count the valence electrons for this one, sulfur has 6, each oxygen has also 6, so a total of 18 valence electrons. And S is our central atom. And if we go ahead and count, we have 6, 7, 8, 9, 10, 11, 12, 13, 14, plus 6 is 20. So let's see, we need a double bond here. So this one is actually one of the cases where, following this method, the Lewis dot structure isn't really a logical one. It's not one that you'd expect. This is actually the final structure, and keep in mind that sulfur has an expanded octet, which means that it can have more than 8 electrons in its valence shell, which is the case here. So it doesn't necessarily follow the rules if you're doing the Lewis dot structure, and it's just one that you have to know and keep in mind. So that's the shape of sulfur dioxide, and this one isn't actually going to be linear because of that lone pair. So what's going to happen, you will see that the molecular geometry of this structure is going to be bent. Because if my fist is sulfur and these are each oxygens, by adding that lone pair, that the electron cloud of that lone pair is going to repel the electron cloud of each of the oxygens and going to push them down, so that we have a bent shape now. We no longer have a linear shape, as is the case with carbon dioxide. So the next step is to determine if one of these is polar or non-polar. So where does polarity come from? So each one of these bonds, this CO bond, is a polar bond due to the large difference in the electronegativity of carbon and oxygen. So these bonds are polar, and carbon is going to be partially positive while the oxygens are partially negative. But is the overall molecule polar? So keep in mind that even if you have polar bonds, doesn't mean that your entire molecule has polarity. So this is the case with carbon dioxide, and that's because these dipole vectors are pointing in the completely opposite direction. So they're going to cancel one another out. Such that this molecule will not have polarity. But in the case of SO2, if I was to redraw it with its correct geometry, it would look something like this. And so the dipole vectors are pointing this way and this way. So in this case, if we think of these as vectors, they have an x and a y component. So the x components are going to cancel out, but the y components are going to add up such that you have an overall dipole on this molecule that points down. So your molecule is a polar molecule. So this one is polar, and this one is nonpolar. Alright. Well, I hope this video made sense. If you still have questions, make sure to come to office hours and attend our workshops on Wednesdays.